Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end, and certainly we'll follow up with any unanswered questions via email. These Tech Talks have been designed to provide straightforward insights into radio frequency components, some of the related technologies, and the extra design and engineering value that is added by a custom manufacturer such as Quantic Corry. To begin today's session, I am pleased to introduce Quantic Corry's Vice President of Engineering, Jim Price. Jim is an electrical engineer, a patent holder, and has written numerous white papers on filter design. He's been with Quantic Corry since 2004, and over the past 20 years, his passion for helping customers and solving problems has only grown in intensity. So welcome, Jim. Can you share an overview of today's topic and your objectives for the session?
Sure. Hello, everyone. So the topic today is tunable filters. I'll be mostly talking about bandpass and band reject filters. Low pass and high pass filters don't seem to be as much of a concern when it comes to tunable filters. We'll get right into the popular tuning elements for these kinds of filters, varactor diodes, and like air core plate capacitors are two possibilities. We'll talk a little bit about those. We'll talk a little bit about the resonant structures that those are used in as the basic building blocks for multi-pole filters, and also the design technique that you use to get to coupled resonator multi-pole filters, end-pole filters. There's a pretty good book, Handbook of Filter Synthesis, I have noted at the bottom of the slide. It goes through the design techniques that you'd want to use for a coupled resonator style filter, which is maybe a little bit different than the typical lookup tables for filters that most people are familiar with. And the reason you would use these is because they particularly lend themselves to using like varactors and variable capacitors to tune the filters.
Well, that sounds terrific. So maybe to get started, could you tell us about how tunable filters are put to use?
Yeah, so there's a lot of different ways that they're used. If we're talking receivers, sometimes you can have a receiver with a sensitive upfront low noise amplifier, and you might have that amplifier might be capable of tuning in several different channels. And if a lot of those channels are present and at a higher power level, you could overwhelm the LNA and get into a nonlinear operating region of the LNA. And if that's the case, it would be nice to have a tunable filter as a pre-selector where you could tune to the frequency of interest and isolate the other carriers away from the LNA to keep it in its linear operating range. A good use in the same kind of thing on the receive end would be for a notch filter would be if you had an interfering carrier. So if you had a powerful interferer that again could overwhelm the LNA, you could just notch it out with a notch filter. And sometimes as you go from site to site, these interferers aren't always at the same frequency. And if you had an upfront tunable notch filter, as you went from site to site, you could notch out the interferer and protect your LNA. And then turning it around in the transmit direction, tunable filters are useful if you have a transmitter that's frequency agile and it might be spraying information a little wider than it should be relative to its bandwidth. And that way you could have a frequency agile bandpass filter track the amplifier or the transmitter and keep any kind of spurs or transmissions outside the band under control. And again, another application for these are really anywhere that you would perhaps have a switch filter bank. Switch filter bank is a bank of fixed bandpass filters in parallel, and you'll have like a single pole end throw switch before that filter bank and a single pole and throw switch after it. Then you can go down through the bank and select, the low band, the mid band, the high band, or whatever you want. That's a way to do it. Or you could substitute a continuously tunable filter in place of that. Sometimes that's better because you get continuous filtering. You don't have crossover regions.
Okay. Now, I've heard you mention the word varactor, and I understand that that serves possibly as a tuning element. Could you maybe define that a little bit more and explain how it works?
Yeah, sure. Varactor diodes are basically variable capacitors when you reverse bias them. So over there on the chart on the right, I'm showing some MACOM diodes. This is a family of hyper-abrupt MACOM diodes. You can see that when you reverse bias the varactor to a high voltage, 10, 20 volts or so, the capacitance drops quite a bit. And when you lower the reverse bias voltage on the varactor, the capacitance increases. So it's kind of an inverse relationship. And you can get ranges anywhere from 2 to 1 to 12 to 1 or better out of a varactor diode. And of course, the wider the capacitance tuning range, the wider the possibilities are for tuning a bandpass filter or band reject filter.
Okay, and I'm wondering, can you share some of the properties associated with filter elements?
Yeah, so it's always good to know what the root properties are of the parts that you're using in a filter, so you understand where your stray capacitances, inductances, and losses are coming from. So on the right, I have a typical inductor model that everybody's used to, winding capacitance in parallel, series resistance, and of course, the inductance itself. For the reactor, it's similar. You have a series resistance, you have inductance associated with the package, and capacitance associated with the package, straight capacitance. Those two usually aren't too big of a factor when you're designing with varactors, until you get to the higher frequencies. Typically, what you're more concerned about is the capacitance of the varactor for a given voltage and the resistance of the varactor when it's reverse biased. And just like with inductors and normal capacitors, that impedance versus resistance sets the Q factor of the part, or the quality factor. The higher the quality factor, the better your filter is going to perform. So and the quality factor, I have the definitions there, but just to put it in simpler terms, it's really the impedance of the capacitor or the impedance of the inductor divided by the series resistance of the capacitor, the series resistance of the inductor. So if your capacitor or inductor had an impedance of 100 ohms at a particular frequency, and it had a series resistance of 1 ohm at that frequency, the Q would be 1. 100 divided by 1 is 1. So that's important to know, because the higher the Q factor, the lower the losses are going to be in your filter.
Well, that makes sense. I've also heard you make reference to a basic resonance a circuit rather. Can you just elaborate a little bit, please?
Yeah, really, this is a circuit I think just about everybody's seen. You have an inductor in parallel with a capacitor. Below resonance, the circuit looks inductive, and above resonance, the circuit looks capacitive. And at resonance, it's a excuse me, it's a very, very high impedance. And so the plot on the right shows what that kind of a circuit looks like. If you increase the capacitance, that peak's going to move to the left. And if you decrease the capacitance, that peak's going to go up in frequency. So if you take that basic resonance circuit, that's kind of the building block for coupled resonator filters, at least bandpass filters. You can convert that into a varactor diode circuit by looking at the example below. So here I have a bias resistor on the diode to put it in reverse bias, an extra capacitor there to isolate the diode from ground. And the inductor provides a DC path to ground for the reverse bias on the diode. And in aggregate, the circuit below is the same as the circuit above, and you would get the same performance that you see in the plot from either one of these.
Okay, now you noted that these circuits were used with bandpass filters. Are there different ones for other types of filters?
Yeah, so this is an example that you would use perhaps in a notch filter or a band reject filter. So instead of a parallel resonance circuit, you use a series resonance circuit, and the principles are the same. You can substitute a varactor and a reverse bias on that varactor for the capacitor, and then the inductor remains the same. And now, as you change the bias voltage on the varactor, the notch is going to go up or down. Higher bias voltage, higher frequency notch, because remember that reduces the capacitance of the varactor.
I see. How about other filter types?
Yeah, so uh, this is really showing you how you would use these resonant structures to make a filter. So I referenced that a book at the beginning. The author of that book goes through in great detail how to create a circuit like this. So basically, resonator A, B, and C are what you're seeing down there in the lower left, the varactor in parallel with an inductor for a parallel resonance circuit. And then the series capacitors from input to output, you'd replace those with the circuit you see in the lower right, a series varactor bias with a resistor as well. That's the equivalent of the series capacitors. And the principle of this basically is to the resonators are the poles of your filter. So in this example, we have a 3-pole filter, and the capacitors couple energy from input to pole to pole to pole to output. And you can make this a 2-pole filter, a 1-pole filter, a 5-pole, 7-pole, whatever you want, depending on whatever order of filter you need. The frequency response is shown in the graph over to the right. So this is ideal. There's a pretty high Q in this. There's really no losses. And so these things look pretty perfect over to the right. And in this example, the lower band pass is centered at 250 megahertz, and the higher is centered at 500 megahertz. And this can be achieved just by varying the capacitances in all those different legs that you see on the circuit to the left. So it's quite a few capacitors to vary, right? You've got one in each of the resonators to ground, and then you've got the 4 in series. So you're varying 7 capacitors in just the right way to get the response that you see over on the right. So this is an example of that same circuit, but now with some practical components involved. So I set the Q of the diodes to between 100 and 200, and that's using real diode examples. Q of the inductor at 100, which is very realistic for this circuit. I set the bias resistors at 10 kiloohms. And the result is the same kind of a plot, but the insertion loss is now 3.5 dB, and the corners are a little bit rounded, as you can see. The other thing to notice is that in this example and the one before, the responses are not perfectly symmetrical, and that is an offshoot of designing in this way. The reason why they're not symmetrical is because there's only one 0 at infinity in their circuit. It doesn't act like a 3-pole filter at infinity. It only acts like a 3-pole filter around the center frequency of interest for each one of these filters. And the reason why, just not to get too technical, but remember how I said the resonators look capacitive above resonance? So if you look at this circuit above resonance, it's a series capacitor, capacitor to ground, series capacitor, capacitor to ground, etc. It's really just a capacitor. And a capacitor provides you 1 0 at infinity. So on the right side of the filter, it trails off a little bit, tapers off a little bit longer than it does on the left side. Now, if those capacitors were inductors, you'd see the opposite effect. And if it was a mix of capacitors and of inductors, it would be much more symmetrical effect. But we're trying to make these filters tunable, and it's really difficult to tune inductors. So you're kind of left with this sort of effect when you go with this coupled resonator approach using all capacitors.
Okay, and what are some of the advantages and disadvantages of designing with coupled resonators?
So the one big advantage of it, of course, is that the inductors are constant. You don't have to fool with varying the inductors. Some other filter creation techniques. You can't just vary capacitors and have the response look good over any kind of a reasonable bandwidth. In this kind of filter, you can. The other thing that's nice about this style is the inductor values can be somewhat arbitrarily chosen. You're not locked into a specific inductor value at a specific frequency for a specific response. You can pretty much pick whatever inductor makes sense for you and then match the varactor that makes sense for that inductor. And that way you can play with the values to get the highest combination of Q factors for your inductor and for your varactor. The other thing that's nice about this is even and odd order filters are symmetrical, or at least they can be symmetrical. And what I mean by that is a lot of times when you're designing filters, if you have an even order filter, 2, 4, 6, 8 poles, something like that, the input impedance and the output impedance are by definition different with those design techniques, and you have to do something at one end to get the impedance back to where you want it to be. With these coupled resonator styles, it doesn't matter what the order of the filter is, the impedance on each end of the filter can be symmetrical. The kind of the negative thing about using this approach is although I said that the impedance can be the same on each side, it does vary as you tune the capacitors. So if you tune the capacitors over a 4-to-1 ratio to get say a 2-to-1 tuning range, that's great, that would work, except the input and output impedance that you would end up with wouldn't be the same as what you started with. You have to vary the capacitances a little bit differently on the ends relative to the ones in the middle to keep your input and output impedance constant. So it's good to know that. The other negative about these things is varactor Qs are worse than pure capacitor Qs. So you're going to have worse insertion loss in a varactor-based tune circuit than you are with than just using pure capacitors. You have to deal with the biasing complexity of the varactors, sticking those resistors in there and throwing reverse biases in and making sure that all your diodes have a DC path to ground. That can be a little bit of a pain. And the other thing is the transmission 0 to infinity that I had already talked about. And tuning usually requires a microcontroller or a DAC or something like that because, as I said, you have to kind of tune the ends of the filter differently than the middle of the filter. So and varactors are inherently not very linear.
Well, okay. And how does Quantic Corry control and package the tuning process?
So to control these things, you can control them as simply as just with a knob, right? A manual analog knob. That when you get to higher order filters or more difficult filters, it can be hard to do because things get nonlinear inside the filter pretty quickly. The other thing you can do is control them with a microcontroller. You can, and once you do that, you can put an Ethernet or USB interface on it, have a web interface, some kind of a command line protocol, and you can command the filter to do whatever you want it to do. And then the microcontroller takes care of all the difficulties of putting the exact correct bias voltage at the exact correct frequency that you're looking for. You can control them with 1-0 IO logic, just TTL or 3.3 volt logic or what have you, parallel or serial clock or latch in commands into the unit to command it to the frequency of interest. Or you could go old school communication style, go with IEEE 48 buses, RS-232. Some of those kinds of things are also definitely possibilities. And then for packaging, at least with varactors, you can get pretty small with them. You can get surface mount with like a little shielded surface mount enclosure, all the way up to, benchtop assemblies. The picture on the right shows a notch filter, and that's controlled by an IEEE 488 interface, and it's a benchtop unit.
Well, some good information. So what else should we know or consider?
Well, so we already talked about the microcontrollers, but with regards to those, what kind of tuning speed can you expect? Well, that depends on the execution speed and number of instructions that you have to execute with your microcontroller, the digital analog converter conversion time, and then just the RC and LC time constants of your filter. Generally, tens of microseconds are not unreasonable to go hop from one frequency to the next. Um, uh, the other important thing to realize is that you have to get varactors with good Q and inductors with good Q, and you need to optimize that during the design process and perform your trade-offs then. Power handling, at least with the varactor base, they're not generally that high, milliwatts to maybe a watt. And the reason why is because you don't want the RF signal to affect the bias of the varactor and have it start to go nonlinear on you, or get out of tune just from the amplitude of the RF signal. These are good up to maybe about 2 gigahertz. It starts to get a little bit more difficult after that with these kinds of filters. And I know I've talked, all about bandpass filters here, but notch filters also apply to pretty much everything that I've said here.
I've also heard you speak about variable air capacitor tuning. What does that involve?
Yeah, so I thought I'd show an example of a notch filter here with variable air capacitors. These capacitor plates move with frequency. If you can see them there, yeah, so they move capacitance getting smaller and smaller and smaller as you move it away from the blades, and now it's getting larger and larger and larger. So you kind of get like a smooth tuning operation like that. So those are blades on a spindle. You can turn that spindle by hand. In this case, there's an IEEE 488 interface on it. There's a motor with a gearbox inside, and that's serving to tune the filter.
Okay, interesting. Now, can you give us maybe an example?
Yeah, so using this example, here's some performance plots that were actually taken from that unit. This one's a notch filter that was designed to operate from 200 megahertz to 400 megahertz. So the plot on the left shows you the performance at 200, in the middle at 150, and to the right at 200. But this thing's continuously variable over the whole range. And you can see you get pretty good performance. This is a 3-pole response, and it's giving you 50 dB of rejection.
Okay, and finally, what are some of the ways in which Quantic Corry differentiates their approach?
Well, we have a lot of experience in designing all different kinds of filters, not just the kinds I've mentioned. And we work with customers to with whatever the requirements are to give them the performance they need. So size, cost, insertion loss, rejection, performance trade-offs. We'll work with our customers to get them the filter that's best for their application.
So in other words, it's not just here's the component, you're providing solutions and consulting value.
That's right. Yeah, we like to help our customers to get to where they need to go.
Got it. So I think we have time for at least one question. And the one that I received here, are there additional ways to make a tunable filter aside from what you've discussed?
Yeah, there definitely are. I guess one thing I'd like to say is the example that I showed showed the bandwidth of the filter varying with frequency. If you remember, the 250 megahertz filter had a bandwidth of about 25 megahertz, and when it got to 500 megahertz, had a bandwidth of 50 megahertz. That was basically a 10% filter. You don't have to do them that way. You can keep the bandwidth constant over the range, but your capacitors need to vary to a greater degree. Instead of varying them at a 4 or 5 to 1 rate, you need to vary it more at like an 8 or 9 to 1 rate. So it gets difficult to have a wide tuning range when you're trying to keep the bandwidth constant. But there are other kinds of filters that are tunable. One big one is a YIG filter, yttrium iron garnet. You use a little YIG sphere to as a tuning element. And it's a tuning element just like the ones I showed you, and they're coupled together just like I showed you. But they operate on a completely different principle. You can tune those over a multi-octave bandwidth. They're a really nice way to go if that's the kind of thing that you need. And they go pretty high in frequency as well. 18 gigahertz isn't out of the question for a Yig filter. And the other thing you can do is you can go with like wavelength resonant kind of filters where you have a comb filter or a cavity filter, and you essentially have a transmission line that's resonant, and you can always put a varactor on the end of a resonant transmission line to tune it. That's a whole different topic, but that's another way to create tunable filters.
Okay, well, additional questions we will respond to via email. And in conclusion, I think that the bullets on the screen pretty much say it all. If you are a customer and you have more questions, we'd love to hear from you, and we hope you'll call our engineering hotline. The number is on your screen, 724-940-7556, extension 276. There are no costs associated with these calls. And going forward, our next Tech Talk will be on Tuesday, March 12th, and the topic will be dielectric resonator filters. So thank you, Jim, very much, and thank all of you for joining us.
Thank you.